With an appropriate phase shift, you can turn an amplifier into an oscillator. I'm Professor Fiore, and I'll explain it to you right now. Hey folks, time to talk about the phase shift oscillator. Essentially, we are going to add an appropriate phase shift to an amplifier and come up with a sine wave. Pretty cool, eh? Here's the basic idea. If we look at the Barkhausen stability criterion, it says in order to have a stable amplifier, there are certain requirements regarding the phase shift around the amplifier and its feedback loop, as well as the gain. And we kind of turn the Barkhausen criterion upside down. In other words, we sort of violate the idea of stability. And if we don't have the criterion met, what will happen is the circuit will go into oscillation. So the way of stating that for oscillation is you want to make sure that the loop gain, in other words, the gain of the amplifier plus the loss through the feedback, is at least 1. In fact, it has to be slightly greater than 1 to start oscillation, but you want it to fall back to unity in order to keep the oscillation going. The other part of this is the loop phase, in other words, through the amplifier and the feedback network, has to be an integer multiple of 360 degrees. So the question then is, what kind of amplifier do we need to get this thing to go? Because ultimately, we only want that set, in other words, the loop phase and the loop gain thing, we only want that to work out in our favor at one particular frequency, right? We don't want the loop gain and the phase to meet these requirements over a whole range of frequencies. If that happens, we're going to have a mess. We just want one network. So usually we do this through some kind of frequency selective network, an RC network, for example. Now, if we choose to use a simple inverting amplifier, right, 2 resistors, 1 op amp, that by itself has a nominal phase shift of 180 degrees. Maybe a little bit off that, which I'll explain in a moment, but we look at that as 180 degrees. So what I would like to do then is add another 180 degrees of phase shift, and that'll give us 360 degrees total, right? We just need an integer multiple of 360. So that'll work great. Now you think about that for a sec. You know, we're going to avoid using inductors because inductors don't really behave all that well in the real world. So we're going to stick with caps. So a single resistor capacitor network can produce a phase shift maximum of 90 degrees. So practically speaking, we would need 3, not 2, but 3 RC networks to get the 180 that we need, right? You say, well, wait a minute, 90 and 90, that's 180. Yes, it is, but the loss produced may be phenomenally large. And besides, as I said, the op amp may not have a phase shift of exactly 180 degrees. So practically speaking, we need 3 RC networks. Now, it's not necessarily the case that you're going to have these set up for 60 degrees apiece. That is not a requirement. You just need 180 degrees total, okay? This particular design we're going to look at is really suited for a single frequency, a fixed frequency application. It's not necessarily all that easy to manipulate in order to get a sweepable, let's call it, an adjustable frequency. Let's take a look. First, I want to look at the phase shift network itself. So here I have 3 sections. Like I said, we need 3 RC values. And I've set them all equal in value. And this is practically speaking the way we would typically do this. If you tried to do a 60-60-60, right, 60 degrees each, and I explain this as an introductory element in the free op amp textbook, right, that you can download, the issue there is you have to make sure that subsequent stages don't excessively load. In other words, the C1 R1 is loaded by these 4 resistors, C2 R2, C3 R3. And C2 R2 is loaded by C3 R3. So you would actually like these values to be, an order of magnitude bigger than these, and these to be an order of magnitude bigger than these. So, you're looking at some pretty big values. In other words, if I was to start with 100 nano and 1K, to avoid loading, this would be a 10 nano with a 10K, and then the next stage would be a 1 nano and 100K, right? So you can see a practical issue here with these resistors getting bigger and bigger and bigger and bigger and bigger. So instead, we do this equal value thing, which is very convenient. When you go and manufacture something, you have all the same size values. So each of these stages will not produce 60, but the whole thing can, in fact, produce 180 degrees, which is what we want, right? So clearly, some of these stages are going to produce more than 60 and some less. Now, in the text, I have a proof of exactly how this all works out, and it boils down into this one formula. Proof is a little on the long side for a video, so I'm just going to give you the formula. And that is the resonant frequency, the oscillating frequency, is 1 over the quantity 2 pi times the square root of 6. And this is the only convenient way I could do that in TINA, 6 raised to the 0.5 power, times R times C, right? So there's your R value, all the same, and your C value, all the same. Now, when we analyze this, what we're going to discover is that at this 180 degree phase shift point, the gain is going to be approximately 1 over 29. So let's do just a simple Bode plot on this thing, just to verify. And this works out to, if you do the calculation, it works out to about 650 hertz. Okay, so on top we have our gain, on the bottom we have our phase. I'm going to grab a couple of cursors here. So the first thing I want to do is find where does this thing hit negative 180 degrees. Let's see, there's 180.6, 180.2, 190, it's right around here somewhere. Okay, now I'm going to go up and grab another cursor and find out what the gain over there is. Okay, I should say loss. That's a negative dB gain. So there I am, my minus 180, and this is coming out to minus 29 and change, just about, call it minus 29.2, whatever. That value, if you turn that value, minus 29.2-ish, back into an ordinary gain, coincidentally, happens to work out to 1 over 29. Or I should say that actually the proof of this, the gain, that the loss that is produced is 1/29th. And if you turn that into a log value, it's a smidgen over the minus 29. So it's about minus 29.2. But this shows us what's going on here, okay? All right, now we verified that at one frequency, in this case about 650 hertz, we will have this phase shift of 180 degrees, but there will be a loss of approximately 1/29th. So I need to make an amplifier with a gain of 29, right, to overcome that, and inverting so that I have the 180 from the inversion plus the 180 from here gives us 360, and we've satisfied our Barkhausen criterion. So let's go look at a little circuit. Ignore this stuff up here right now. So here we have an op-amp, RF, RI, so we know that this is an inverting amplifier. Notice RI is going into the inverting input, okay? And you're going to say, hey, wait a minute, that's 36K and 1K, that's a gain of 36, that's not a gain of 29. Yes, that's true, and there's a good reason for that, which I'll get to in just a sec. But the other part of the op-amp, the other part of the circuit, we see the output going through the RC network that we looked at just a moment ago. However, right, going through this. However, this is actually drawn in reverse, right? Because this is the input to the feedback network. Feedback is going this way. So notice I've labeled these as C1, R1, C2, R2. C3. There would have been an R3 here, but it turns out we don't need an R3 because we have Ri. How does that work? Well, normally you would have R3 out here. In other words, this one, right? Here's the cap, and there's R3, and there's the output we're interested in. Okay. Now, off of C3, we have this Ri. But this is going to virtual ground, right? That third resistor was going to ground, right? So it's the same. This is going to load these other elements just like the original circuit did. And ultimately, right, that current that flows through this Ri is the same current that would have flowed through the old R3 in the preceding circuit. So we can save ourselves a resistor. This kind of does double duty, all right? It takes that voltage, turns it into the current that feeds the op amp, and off we go. Okay, so we already know about this network, all right? We already know about the inversion of the op amp. So then the question becomes, hey, why did I use 36K instead of 29K? And yeah, there is an issue in practicality with, tolerances, right? That is true, but that's not the main reason why we're doing this. The real reason is associated with what's going on up here. So I have a pair of back-to-back Zeners. These are 5.1 volt Zeners. So when the signal gets up somewhere in that several volt range, what's going to happen is, let's say we have a current going in this direction, right? A plus to minus. This Zener is going to be forward biased, and this will go into Zener conduction. Now, at a really small voltage, in other words, if we only have like, a few tenths of a volt or so across RF, these things are off. This is a high impedance. We don't really see anything. But as the signal starts to increase, we start to get more and more conduction through one of these two diodes, all depending on, the polarity of the RF voltage. So like I said, one's going to be forward bias, one's going to be in Zener conduction. But in Zener conduction, a Zener diode can actually be hauling a fair amount of current. So what that winds up doing is it places whatever this effective Zener impedance plus this other resistor over here, which I'm calling R3, it places that in parallel with RF. What does that do? That lowers the effective value of RF. So as the signal increases, RF effectively gets smaller and smaller and smaller because the bigger the signal is, the smaller this net impedance up here is. And therefore, putting it in parallel with RF makes that result a little bit smaller. So this kind of eventually, let's say, settles on a value that will give us just the proper forward gain that we need. All right. Now, earlier I mentioned that, we don't necessarily worry about getting exactly 180 degrees here. Our formula, the 1 over 2 pi with square root of 6 RC thing, sort of assumes we need exactly 180, but in reality, the op amp itself will produce a few degrees of phase shift beyond. In other words, it's ideally 180, but once you start moving up in frequency, the phase of the op amp itself starts to continue, right, with the feedback. It doesn't stay at minus 180 forever, right? So in fact, because of the, let's just say, a few extra degrees, that's going to shift what we really need down here. But this will, like I say, sort of self-select, because there will only be that one frequency that gives us the appropriate gain and the appropriate phase shift, right? Because we just need 360 total. All right, so this is probably, for the most part, going to be designed empirically. We know rule of thumb, like I'm not going to put like a 15 volt Zener up here because I only have a 15 volt power supply. But you're probably going to just play with these. If you're in lab, monkeying around, you can put some values in here, try different values for R3, again, depending on tolerances and whatnot, you might find a slightly better value for your value of RF. But basically, this thing should settle in on this one frequency. So we, by formula, predicted this would be like 650 hertz. So let's go do a little transient analysis over here. And I'm delaying the analysis, the simulation, to get away from the initial startup, right? The transient startup. Okay, so there we go. You can see this is a relatively nice looking sine wave. You know, I mean, it's not a perfect sine wave probably, but it's not bad. And it's coming up to about 5 volts peak. All right, so, you know, when the signal's getting up like here, that's when these zeners start to turn on. And it's getting just a little bit of current through here. You know, you're putting this whole resistance, like I said, whatever the zener resistance works out to be plus R3, you're putting that effectively in parallel with this RF, just enough to bring this down to give you the gain that you need, right? Well, you know what's going to happen. Down here, there's really no effect, but as you go up, that effect gets greater and greater and greater. And that's going to slightly distort your sine wave. Now, like I said, this looks like a pretty nice sine wave. I mean, it's never going to be perfect because of the number of points we have in the simulation, but, you know, it looks like a halfway decent sine wave. Well, how can we check just how good it is, right? I mean, you can always go in and, you know, zoom in and say, well, that looks, you know, pretty good. All right. You could take the time to accurately measure what this frequency is, which, no surprise, I did. And then you can come back in and do a little Fourier analysis, all right? So instead of doing our transient, we'll come in here and do a Fourier analysis and just set this base frequency to what you calculated. In other words, what was measured out here with your cursors. So I measured 640, and like I said, it's not exactly 650 because of the little phase shift extras that we're getting from the op amp. Off we go, all right? So now I'll just do a calculation. It's going to use 640 as the base, and then all the harmonics will show up, right? We'll see what the harmonic distortion is. Womp. All right, so this opens up. You can see that the first harmonic, right, the original 640, that's just about 5 volts. And then we have, you know, millivolts, tiny little millivolts for everything else. And the total harmonic on this harmonic distortion, the total THD, is about 1.25%. All right, so that's nothing to write home about as far as a super low distortion source. But if what you need is just, you know, a little source to test things, it's great. Or if you just need a little, you know, like a beeper noise or something, this is fine. This is great. You know, you could run this on a couple of 9-volt batteries. You know, if I was going to do that, I would probably change the zeners up here, get something a little bit smaller. Otherwise, you know, you might get a little bit more obvious kind of a distortion. But this is, you know, perfectly good. It's a perfectly good source. Now, I also mentioned this is designed for fixed frequency. If you look at this, there isn't a really convenient way to play with the frequency, you know, with like a single pot. There are some other videos that we have, you know, regarding adjustable, sweepable sorts of signal generators. This is really not one of them. If you think about it, you know, you could theoretically take R1, R2, and Ri and get like some kind of triple, quadruple gang pot, right? But you also have to adjust the value of RF because this and this are tied together for the gain part, but this is also being used here. And you're going to be hard pressed to try to find any kind of adjustable capacitor, right? You can find, you know, adjustable capacitors, continuously adjustable caps, but they're small values. They're picofarads typically. You know, you're not going to see stuff up here in the, you know, hundreds of nanofarads. All right. So that is a limitation of this circuit, but otherwise it's fairly simple. It's straightforward. It's relatively stable. And ultimately it works. It does what you need it to do, right? It produces a halfway decent sine wave that's just going to sit there, decent amplitude. In this case, like I said, we're getting 5 volts. It's got all the output current capability of whatever op amp you choose. There you go. It's easy enough to calculate new values. Oh, you know, you could, by the way, if you wanted different frequencies, the easy way to do that would be have multiple sets of caps and use, you know, a multi-gang switch. So you maybe have, you know, a set of 300s and then a set of, you know, 3 470s and a set of 220s or whatever it is that you're interested in doing, and you could have discrete frequencies that you could change. It's just that trying to get continuously adjustable frequency, not so easy, but still a good usable solid oscillator. Okay. All right. Well, this is Professor Fiore. I hope you got some good info out of this, a little bit more understanding on how these oscillators work. And until next time, take care.